My name is Dr. Sachin Borse. Presently, I am Professor and Coordinator International Relations, Imperial College of Engineering and Research, Pune, Wagholi, India. Today, I will talk about the internal flow. I will specifically discuss the laminar flow in the duct. Now see the tube or the pipe having the radius r and fluid is flowing through this, and this flow is laminar. Now as we know that to derive any equation we start with some small element. Consider the cylindrical element A, B, C, D having the radius small r. You can see the radius small r. Then this capital R is the radius of the tube. Now this element is subjected to the forces. Normally in the fluid flow there are the three forces. First one is pressure force, then viscous force, shear force you can say, and third one is gravitational force. Now in this horizontal pipe, as we are considering here along horizontal as x direction, and I will write Newton's second law, which is about the forces. In this x direction there is no gravitational force, so basically there will be only two forces. One is pressure force and second one is the shear force. So what is the Newton's second law? It tells that summation of forces is equals to mass into acceleration, that is m into a. M being the mass of the element and a being the acceleration. Now in this case for steady fully developed flow, the acceleration will be 0. So basically this Newton's second law becomes net forces, so summation of forces equals to 0. Now if you see the diagram, there is a pressure P is acting from the left hand side on the area pi r square, that is cross sectional area of the pipe. And on the right hand side, what is the pressure? The right hand side of the element pressure is calculated by means of the Taylor series. So pressure, the two faces, left and right face of the element are separated by the distance dx. So the pressure on the right hand side becomes P plus del P by del x into dx. Okay, now pressure into the area is pi r square, so pressure into pi r square, pressure force on the left hand side. Similarly the pressure into the area on the right hand side, we can find the pressure force. Now there is third we can say second force is what? Shear force. So shear stress tau into the area, that is the outer surface area of the element, it will be perimeter into the length. So perimeter is 2 pi r into the length, it is dx. So we get the shear force. Now we write summation of forces equals to 0. Here summation means algebraic summation, the summation with sign. So pressure force on the left hand side is along the x, so it is positive. Pressure force on the right hand side It is negative because it is opposite to the x direction. Similarly, the shear force on the surface is opposite to the x direction, so it is a minus. So rearranging this, we get the shear stress tau is equals to minus r by 2 del p by del x. So one more equation for tau shear stress is from Newton's law of viscosity. Now see the diagram shown in the figure 2. It shows the shear stress distribution on the left hand side. You can see the shear stress is 0 at the center line. It goes on increasing and it becomes maximum on the wall of the pipe. Similarly, you can see the velocity on the right hand side. Velocity is maximum at the center line and it goes on decreasing, and on the wall it becomes 0. What is that? It is a no slip condition. Velocity of the fluid on the wall of the tube is 0. Now from the Newton's law of viscosity, shear stress is equals to tau is equals to mu du by dy. Du is change of velocity in the radial direction and dy is a distance, change of distance from the wall. So earlier we took the distance from the center line, but this Newton's law of viscosity requires the distance to be measured from the wall. So y will be equals to capital R minus small r. Now we have to replace, we have to write dy, so take the derivative of this. When we take the derivative of this, it becomes dy equals to minus dr, where capital R is constant, so its derivative is 0. So we get tau is equals to mu du by minus dr. So you put this tau value in the earlier shear stress equation, we get the equation of du, change of velocity. Now from this equation I can find velocity u at any radius r from the center line by taking the integration. Now our interest is to find velocity at any radius r. So what we do, we take the integration. After taking the integration, I get 1 by twice mu dp by del p by del x r square by 2 plus c. What is c? C is the constant of integration. So how we find this c constant of integration? By applying the boundary condition. We know that at r equals to capital R, that is on the wall, there is a no slip condition. No slip condition means what? Velocity is 0. Now by putting this r equals to capital R, we get u equals to 0. So from this we get the value of c, that is minus 1 by 4 mu del p by del x r raised to 4. Now you put the value of c and then you get finally the equation for velocity small u at any radius small r. This will be the equation 1. So if you observe this equation, you will get that del p by del x is constant, r, capital R is constant, and mu is also constant. So basically the velocity u at any location r from center line varies with the square of the radius small r. So it is a parabolic in the nature. So if we plot this velocity in the section, longitudinal section of the pipe, we will find it as a parabolic. Now we want to find what is the velocity at the center line. It is a maximum velocity, so I will write u as umax, the velocity as a maximum. So if you put the value at the center line, r is equals to 0, so you get umax is equals to 1 minus 1 by 4 mu del P by del X R square